Let me start with the definition of angular velocity of a rigid body. Angular velocity of a rigid body, that is the differential kinematic step to define the motion, differential motion of a rigid body or a robotic manipulator arm. First of all, angular velocity is an attribute of the whole rigid body. It means that if we have a rigid body, the all point within that had the same angular velocity. This is different from linear velocity, that is an attribute of a point within the rigid body. And the definition is very simple. We had the rotation defined as a screw vector. We have defined a rotation of a rigid body as an angular motion of a rigid body along a vector. We define angular velocity as the derivative of the rate of instantaneous rotation of the frame B attached to the rigid body with respect to a fixed frame B. With this, in this term, if we discuss that, we'll see that this instantaneous is very important, since during the rotation the vector is also changing. But the angular velocity is simply defined. We define it this way in a screw-based coordinate, which is very, very important and shows the importance of the screw axis definition we have before. Then we relate it to the other aspect of angular velocity and rotation and other angles and other stuff that we discussed before. So basically, we define angular velocity as the rate of rotation, we call it theta dot, along the previous same axis of rotation, which was s hat. And this is physically very sound because we have a rotation, we had a rotation about a vector, and this vector, of course, the angular velocity should be along or about this vector as well. So this is a vector. Angular velocity is a vector. The direction of the vector is basically the same, the old same screw axis, or the rotation, the axis that we rotate about it with the right-hand side definition or notation. And the amplitude or the magnitude of rotation is how fast is this rotation happening, which we call it the theta dot. So angular velocity is defined as theta dot times s hat. Now, this vector rotation can be represented in any frame. This is a real vector. This can be represented in frame A, B, or any other rotation. So if we basically write it in frame A, the reference frame A, it has three components. The components, we call it omega. I used intentionally I used large omega sign here to distinguish between the some other rotation matrix. If we call it omega or a large omega, then we have basically this idea of angular velocity of the whole rigid body. And as you see here, the rigid body can be represented as omega x, omega y, omega z as the component, and these are nothing but sx, sy, sz, the component of the vector that we have. The amplitude is given by theta dot, and the vector is given by the screw axis. So almost in no other reference the definition is given this way, but they are given in a very more difficult way. Let's see how the difficulty it is. We saw that angular rotation angular motion can be represented by a rotation matrix. Is angular velocity related to the rate of rotation matrix? Is it the rate of rotation matrix. It is related, but it is not the rate of rotation. Let me start with the rotation matrix. So the question is, what is the relation between the angular velocity omega and rate of rotation matrix r dot? We start with this general property of rotation matrix. We know that the rotation matrix is an orthogonal matrix. So R times its transpose is the unity matrix I, or R transpose is the inverse of the R. So we will differentiate from this equation. Since this part is I is unity matrix, the derivative will be 0, then we have two parts here. And derivative of the first term multiplied by the second term, and the first term multiplied by derivative of the second term. Very good. Still, this is not very easy to comprehend. Let's start with some other properties of the rotation matrix. We know that transpose is the inverse for any orthonormal matrix, and also the inverse transpose, if we make it an inverse transpose, will we go back to the first rotation matrix. So we have RP with respect to A inverse, and transpose goes to the same angular velocity here. So if we use these two, now consider this one as before. Instead of using this one, we use this part, and to have this part, we use a transpose for both of them. When we transpose this comes first, and the second one has a transpose, but we can use the transpose, we can just use the inverse instead of the transpose. So by some manipulation, very simple manipulation here, we come across to a very significant point. As you see here, call this matrix as U, R dot times RB with respect to A inverse, R dot times R inverse, call it as a U, as a matrix, plus U transpose, the same transpose is equal to 0. A matrix plus its transpose is equal to 0. This means in linear algebra, that this matrix is a skew-symmetric matrix. Skew-symmetric matrix is a matrix that has 0 on the diagonal matrix and negative sign on the off-diagonal matrix. And just for a few minutes, agree with me and consider my claim that the off-diagonal matrix elements are nothing but the angular velocity components. Omega z, the same omega z that we have here, omega y and omega x. So this matrix R dot times R inverse is, for sure it is a skew-symmetric matrix, but I claim that this is the skew matrix, this is the skew-symmetric matrix that is related to the angular velocity by this component, as you see. Now, this can be proven in many ways, and if you look into different books, this proof has been given different way. But I will use another very important rule to just prove this part. Now, we call it omega x because of some reasons. We have a omega x on upper bar because we can see that the cross vector multiplication can be represented as a matrix manipulation with this. I will go through that in a few slides. But this omega x has also one other meaning that I will give you in a few minutes. Now, We know that this is a skew symmetric matrix. Now, let's see how this is related to that. To do that, just give a few minutes. Let's think about angular velocity and Euler angle. Why we don't use Euler angle or quaternion or other means of representation for angular velocity? Why we use just the screw term? As you see here, the main important one is because angular velocity is a vector, but Euler angle are not. What does it mean? We saw before that Euler angle is not a vector because we don't have the commutative adding, changing the vector properties of a vector angle. And also angular velocity rate is not, definitely not, the angular velocity. Let's call alpha, beta, gamma any kind of Euler angle that we have. And the rate of it as alpha dot, beta dot, and gamma dot, we can instantaneously check how alpha is changing, beta is changing, and gamma is changing. And in many old papers and in many issues, we can find this problem, this mistake, that they use this angular Euler angle rates as the angular velocity. But this is not true. Consider this is not true, and that's why Euler angle is a bit different and a bit difficult, more difficult than screw axis in the representation of differential kinematics. We can show that there is a relation between omega and angular velocity and Euler angle rate, but these are related with a configuration dependent or nonlinear relation matrix. We call it E. And this E can be simplified, not simply, can be defined by this relation that we have found in previous term. We know that omega dot is equal to that. If we consider that omega dot is equal to that, and this omega is still our angular velocity, accept my claim that this is the angular velocity, then you see that we can find it this way. So any Euler angle from any type of Euler angle, we have 24 different type of Euler angle. We can find a rotation matrix. If we have the rotation matrix, the inverse is very simple. It's just a transpose. And also the derivative is just term by term derivative of the angle that we have. Cosine of alpha, for example, is sine of alpha dot and something like that. So if you use that, we have two rotation matrices. If you just multiply by these two together and factorize alpha dot beta dot gamma dot from this rotation matrix that can be represented by this derivative in component wise, I prefer to use this part, but if you like to use also the component, well, this is also possible to do that. And if we do that, then we can factorize alpha, beta, gamma and find the E matrix. This is a usually difficult manipulation at the beginning, but it comes out with a very simple result usually. For example, for WVW Euler angle that we have given you the R before in the previous chapter, do this manipulation. This is the R matrix. Do the manipulation. Find the R inverse as the transpose and R dot as the simple derivative of all the terms, which is quite large. It will become very large matrix. But at the end, when you do the manipulation, the E matrix would be quite simple. With respect to alpha and beta, and it doesn't have any gamma value in there, which is physically consistent with the properties that we would like to find. So we don't use Euler angle in differential kinematic. I don't say that no one use. Many people use Euler angle in differential kinematic, but they should bear with the difficulty of finding E and using this E in all the derivatives. And remember that E is configuration dependent. Is like something like this, and it has also its own derivative. If you would like to find the second derivative, the derivative of E comes into the picture. But when you talk about screw axes, it is much more simple. Exactly what we have is angular velocity is the rate of screw axis rotation. Anyways, this is also another part. I would like to go to the golden rule, especially for non-mechanical student, for electrical student in computer science. Let's see what is the golden rule. Still, I have not proven my claim, but I will prove it in a few minutes. I will talk about linear velocity of a point. Linear velocity of a point is not an attribute of the whole rigid body, but each point at a rigid body has different velocity. So it's point-wise. It is different from angular velocity. And we define it very simple as the derivative of the position vector with respect to time, or the rate of position with respect to time. But this position should be considered with respect to a fixed frame. I told you that we don't have a completely fixed frame in the universe because everything is moving, but just considering, for example, for a robot, a fixed frame which is on the Earth. Now, if we have this, this is very important. The definition is given with respect to a fixed frame. I use a notation here, fixed, to emphasize that the definition of the velocity or absolute velocity of a point is with respect the derivative with respect to a fixed frame. Now, what if we would like to have a relative velocity? If we make the derivative with respect to a moving frame, for example, we have a fixed frame, we have a moving frame, we make the derivative with respect to this moving frame here. When we do it that way, we call that a relative velocity, which is much simpler to find. But it is not the real true velocity. And to make the difference in the notation, I use the partial derivative notation instead of the real derivative rotation to make sure that basically we would like to have the absolute velocity in terms of this kind of derivative with respect to a fixed frame. Now, what is the relation between these two when we have a derivative with respect to a fixed frame and have a derivative with respect to a moving frame? So we have a fixed frame A, we have a moving frame B, and we have some sort of rotation between these two. We can call it with R, A with respect to B. We can have a angular velocity with respect to this. And this golden rule, of course, this is also proven quite rigorously in classical mechanics, that if you want to have the derivative with respect to a fixed frame, you can make it simple and find the derivative with respect to the moving frame, whatever here it is. Either it is a point position, it is a velocity, it is force, it is torque, or even it is a rotation matrix. Anything that you would like to make the derivative with respect to a fixed frame, to find the real rate of it with respect to fixed frame, you can find it with respect to a moving frame, plus you have to add one term. You have to add to correct the rotation or the angular rotation that you have between these two frames, and we can add this with this position, omega cross that vector. For example, dp, the position with respect to dt, is partial of p with respect to t plus omega cross p, the same position p, omega cross. And this is a vector notation, and we have a cross multiplication here that you are familiar with that. And how we can do the cross multiplication, you can do it different time, ijk, omega x, omega y, omega z, px, py, pz in a matrix, and do the manipulation. And you can see that this can also be represented by omega x, the same old skew-symmetric matrix that I represented here. If you can just multiply that with the vector like px, py, pz, will give you the cross multiplication here. You can also check that after the class if this is right or not. So we can write a vector rotation or a matrix rotation. And in robotics, we prefer matrix rotation since we use the rotation matrix as a simple manipulation matrix. Now, this golden rule, consider that. We use that several times in higher order differentiation. And why it is important for us to do using the moving derivative, because usually we have a multiple number of lengths in a robot, in a serial robot. And it is very difficult to find the derivative of the last link with respect to the first frame. But it is very simple to find the derivative of the last link with respect to its own frame, which is a moving frame. So usually this moving frame is found very easily, and very simple and also systematic, and then we can use this approach to convert it to the fixed frame and find the absolute velocity. And importantly, we are working with absolute velocities always in the differential kinematic, and we need to have this for every point of interest that we are using. Very good. So if we use that golden rule notation, then we can prove our claim that R dot times R inverse is omega cross. This is the one type of proof that can be given there. We use the golden rule. We use the derivative of the rotation matrix instead of the vector. The rotation matrix derivative, the real derivative or the absolute derivative of that is equal to the absolute, the moving frame derivative with respect plus omega cross R. So, and we know that the rotation matrix with respect to a moving frame, when we are sitting on a moving frame, we don't see any motion. So this part is equal to 0. So the derivative of the rotation matrix is equal to omega cross R. R dot is equal to omega cross R. And this is the same thing if you bring it here, the inverse, bring it here from the right-hand side. Omega cross is R dot times RB. This means that the screw matrix that we used here, and I claim that this is the angular velocity of frame B with respect to A, is exactly angular velocity that we can see in here. Now, all the properties are get together. I just want to stop here to have some questions and maybe some comments if you have here. Let me also close a bit my window. It is becoming very, very cold here. Is there any questions up to here? hopefully nothing. So everybody, or this means two things, or I explained so well that everybody has understood everything, or no one has understood nothing, that there is no question. I assume that the first case is true. Do you have my voice? Very good. So I go through very simple preliminaries here. Not simple, the most significant one, I can say. And just to review, first, definition is given by the screw. The relation between R and omega is given by a skew symmetric matrix. We know that Euler angle rate is not equal to the omega, and we should find an E matrix, a difficult manipulation to find the E matrix. And we have the most significant part of this is this golden rule, that derivative of anything with respect to a fixed frame is the derivative of that with respect to the moving frame plus omega cross that issue, or that stuff that we are making the derivative, either in a vector or in a matrix way. And in matrix way, we need to, instead of having omega x, omega y, omega z, we should write this into a skew symmetric matrix, omega x, omega y, omega z, in this form, to find the derivative. Now, here it becomes a bit more challenging, but very, very interesting. What about the position vector of point P? Now we would like to find the linear velocity of a point, as we have discussed before. We have the derivative here, we have given the general rule here, but what would be the real one? We find in the kinematics of a system that point P, if we have the point P, we could find a relative position. We call it P with respect to B, and with the rotation matrix, we bring it into the frame A, and then we should add also this POB with respect to A to find the derivative here. So the position vector consists of two parts: the moving frame relation and the orientation. And this is very exactly related to the Schall theorem that gives that a general motion is divided into two parts, the translation plus a rotation that we have seen before. Of course, not in a screw-based. Now we are using a classical method. Now, if we would like to find the derivative here, we should make the derivative, we should differentiate this equation, and we use the golden rule for the differentiation. Very simple. We say that, okay, the derivative of the first term, P dot, we call it V, with Vp, V sub P, the velocity of point P with respect to reference A, which is PA, is POB dot. POB dot is the velocity of OB, or the origin of the frame B, which is also a point in the space, which can be found very simple. Plus, now we have the derivative of this two part. We can say the derivative of this times that, and the derivative, and this time derivative of that. And this derivative of P with respect to frame B is different from the derivative of P with respect to frame A. This is the absolute velocity. This is the relative velocity, since we are measuring the P with respect to to point B. So this gives you a general relation between the relative velocity and absolute velocity. It comes into three parts. Here we have two components. Here we have three components. And very simple, and this is important, that R dot is the main contributing term here, and we have find R dot here, omega cross R. And this will reduce this relation to this very important rule that we can highlight it here. V of P, this R dot will be omega cross R. Very simple, omega cross R, RB with respect to A, and omega is the angular velocity of frame B with respect to frame A, and this gives you the whole relation here. We have from the relative velocity, we can go to absolute velocity with this three term. This is for a very, very general point in the space, but usually we have this point P embedded in the last link. We have one point P like a center of mass or the end effector point within the last link. This means that this point P or PA is a fixed, relatively fixed, so we don't have any relative motion. If this point P is embedded in the rigid body, the relative velocity is 0, and this three-term relation will be reduced into this two-term relation, and we use usually this one if the P term is embedded in the system. But if the point P is not embedded, it's like a pin that can move in around something, then we have all these three equations. We will use this also several times to find the Jacobian matrix that we will discuss before. But the important issue here is just use simple derivative and golden rule. If you want to find the derivative of very difficult equation, very sophisticated kinematic vector loop closure vector, we want to make the derivative, just make the differentiation and use the golden rule. Whenever you have R dot, use omega cross R, and this will help you to find the differential kinematic quite easily. What about screw matrix and screw coordinates? Now we come to a very important issue. We call it screw coordinates. Screw coordinates, we know, let's see about the, remember or remind you about the screw representation. You remember that the Schall theorem, that general motion of a system can be represented by a rotation theta about S hat plus a translation S0 or D, this vector S0 or D along the S hat, which S0 is a point embedded on the S hat. I would like to discuss some more issues on S0 here. Just look at the S0 and importance of S0 here. First of all, we call screw axis, and in a screw axis physically, when you have a screw, and a bolt, you have a pitch angle. When you turn the screw one complete term, you have a motion of the bolt, let's say 1 millimeter or 2 millimeter. It depends on the pitch of the screw. فاصله دنده ها در اون pitch. The difference between these two, we call it the pitch. We can denote it by a pitch, lambda, which is the amount that we move translationally when we have the rotation of the complete rotation. This pitch lambda is defined by D divided by the theta, the amount of motion with respect to the angular motion that we have, linear motion with respect to that, or more significantly or importantly, we can find the derivative of D dot with respect to theta dot as lambda. There is no difference we use in position or in the velocity. And this has a basically lambda meter per radian. I write it somehow difficult here. This is wrong. Meter per the diameter unit. meter per radian. It means that when how much, if you have a 2 pi rotation, how long this will move along. It has a unit vector of meter per radian. I will fix that. Okay, now that we have the pitch, we have the translation, and we have the rotation, we are defining a new concept, which we call it twist. This is a 6 by 1 vector, or tuple, let's say. We have usually 3 by 1 vector, like position, acceleration, force, torque, everything that we have used to it has only 3 coordinates, x, y, z. But now we are talking about something which is 6 by 1 coordinate. And it's important for robotic because usually we have 6 degrees of freedom. We have a motion in 3 position and 3 angular velocity. And we would like to embed these two together. We have one, we don't call it a vector, we have one twist or screw coordinate, which is 6 by 1, is a concatenation of 2 vectors. The first vector is S hat, and the second vector is S dot, S0 cross S hat plus lambda S. I will discuss about that, why this is coming to here. The main issue is that this vector has 2 parts. The first 3 component is related to rotational motion, and the 3 last part is translational motion. The same thing that we have in Shaw. Rotation plus translation, and we can concatenate these 2 vectors together. This is the definition. We call a unit screw coordinate, a unit screw coordinate, any screw coordinate, a 6 by 1. And this is a concatenation of a pair of 2 vectors, S hat and this vector, which S0 could be selected on any arbitrary point on the axis S. Any point S could be considered as S0 in here. Why this is important? This is unit screw because it still doesn't have the theta dot or theta and d angle. It doesn't have the motion representation, and we call it unit. We can have a non-unit vector screw here, which we call it twist, basically, a 6 by 1 tuple. The 6 by 1 tuple, we call it twist as a vector of the angular velocity of the rigid body plus linear velocity of a point P. So if we put both of them together, this is called twist, and it's called the screw coordinate. Now, this is not a unit vector. It has a amount of q dot here. You consider that this is defined in differential kinematics in velocity vector. Angular velocity, linear velocity. Angular velocity at the top and linear velocity at the bottom. And this is defined by a unit screw coordinate as we defined before times q dot. And I would like to show that this, if we multiply q dot to this definition, if we multiply q dot to this definition, we reach to angular velocity and linear velocity. The angular velocity is very simple. Look at that. If we have q dot times s hat, q dot times s hat, by the definition of the angular velocity, the first slide that we have here, q dot times s hat gives you the omega, gives you the angular velocity of the rigid body. So the first part is quite simple. S hat times theta dot gives you the omega. Omega of frame B, or omega of the moving platform with respect to frame A. But the second part is different and is a bit more difficult. Let's see What is S? Why we use S0 times S hat plus lambda S hat? What this comes so difficultly in the picture? What does it mean really? Let's devise that term by term. So we have S0 cross S hat plus lambda S hat times theta dot. So we multiply theta dot here. You see that this is omega S dot, and this one lambda theta dot S hat. And lambda theta dot, as you see, lambda theta dot is D dot. Lambda theta dot is D dot. And we have S0 cross omega. We can just interchange the position here in a cross multiplication. It gives you omega cross minus S0. What the hell is this? And how important is this? So we have minus S0. This was S0. When we have the point P, A, B, C, this was S0. Minus S0 is this direction. This means that P of OA, this vector, P of S0 is P of OB with respect to A. The position of opposition OB with respect to A, but minus S0 is the position of A or A with respect to B, this point. What does it mean? This means that the second equation gives the velocity of this particular point P, which we have put our base frame on it. Just simple omega cross POB plus D dot S. This is, as you see in this equation, this gives you the velocity of this point P, omega cross D plus D dot times S. What does it mean? And how we can use it in screw axes is very simple. This is like that. I brought an apple here to give a better flavor for a twist angle for you, with a very good smell of an apple. We have a green apple, and we want to find the position, the velocity of this point P here. How we would like to do, how we could do that with this definition. Maybe this side would be much harder. I have proven that. Let's go through how we can use it. Very simple we can use. We have a frame, let's say fixed frame here, x0, y0, and point P. This object, this rigid object, this apple has been moving in the frame, has moved from here to here and has rotated. As you see here, we have a rotation. As you see, we have a rotation. This has been rotated. Consider that the rotation is along this axis and with this rotation. And then we would like to find the position velocity of this point P. What it does say, it says that it is very simple to do that. If you want to do that and use the screw coordinate, just consider an auxiliary or an instantaneous fixed frame on the point of interest. Your point of interest is P. You want to find the velocity of P. Put a instantaneous fixed frame. What does it mean, a fixed frame? The fixed frame means that it doesn't rotate. It has the same coordinate x0, y0, and z0. As you see, x0, y0, and z0. But not at this point. This point is not of our interest. The point of interest is this point P. It was here. Now it has been moved to here. You have x0, xy, x0, z0. And then, if you look at that, this gives you the S0. From fixed frame to this frame, it gives you the S0. And as you see here, minus S0 gives you the position of P. Minus S0 is the position of the point P that we would like to use here. So by using that, the angular velocity and the linear velocity of the point will be very simply defined by q dot times s hat. For a moving frame, for a general moving frame that we have, this first three part, q dot times s hat, gives you the angular velocity, and the second part gives you the linear velocity of point P. By this means, we have the twist angle defined as angular velocity and linear velocity by this means. Now, let me just give the simple cases that we usually use. We use usually only this frame, but I would like to give you the whole idea here. We have usually in robotics either a revolute joint or a prismatic joint. For pure rotational joint, if you have consider we have a very rotational point, as you see here. We have a disk that is rotating about the axis here. For pure rotational joint, lambda is equal to 0. Lambda was the relation between the translation to the rotation. Since we have only rotation, lambda is equal to 0, q dot is equal to theta dot, and the twist representation, since lambda is equal to 0, this part goes away. We have a simple screw axis which has only two parts, S hat and S0 times S hat. And the important thing is about S0. Where is the S0? S0 is the point that you would like to find the velocity of it. So consider that we have a rotational matrix here. We had a rotation, we had a fixed frame, x, y, 0, like this. We have a rotation here with theta dot. Along this, we have omega about this angle. And if this is the point that is of our interest, we put an instantaneous fixed frame on it with the red one, as we put it on the apple. We put it on this plane, put on this point P, and then we use this part for pure rotation. S times theta dot gives you the omega, and this gives you omega cross S0, and omega cross S0 is omega cross R. And you know from classical mechanics that the velocity of that, Vp, is omega cross R. Omega cross R gives you the velocity of the point, and omega gives you the angular velocity of the disk. So we have, by this definition, we have angular velocity of the disk plus linear velocity of a point P, which is in difference, we can use it as 0. We put the frame, the fixed frame on that point P to find this. So this gives, as we defined here, the twist angle. Angular velocity of the rigid body, linear velocity of the point P. And the point P, the point of interest, if we want to find that, we should have S0, and S0 could be found by just putting the frame, the coordinate, the fixed coordinate frame on top of that. What about pure rotational translational joint? If we have only a prismatic joint, not a revolute joint, if we have a prismatic joint, then we don't have any rotation. The screw axis will be much simpler. We can say that lambda is equal to infinity, but q dot is equal to d dot. We have a limit that the q dot is equal to d dot. And this general formulation can be simplified to a simple coordinate, that there is no angular velocity, so here becomes 0, and the linear velocity is along d dot. D dot times S hat. And as you see, if we have a point of P is of our interest, like here, we put a fixed frame here, we had the fixed frame here, we put the fixed frame here, and we know that the velocity of the point P is along the S hat, along the way that we define the S hat with the amount of D dot, and omega P is equal to 0 of this point, but that v of this point is equal to d times s. So we use this coordinate or this coordinate as a twist angle for serial robotic. If we have a very more complicated case, then we use this general twist coordinate. So here I have finished the preliminary part. I would like to have some more discussion with you about the details here. Some part of it needs more thinking and needs more elaboration and practice, but usually we have general issues discussed as we have discussed in here. Any questions? Did you follow my thoughts and presentation?
Doctor?
Yes.
Are you hearing me?
Yes.
Yes. I have two questions, please. In slide 10,
yes.
The derivative of RBA, the derivative of RBA with respect to the moving frame is zero. Is zero?
Yes. But this is not the moving frame. This is, yeah.
Yes, no. You said that because we are the one who is sitting in the moving frame will see that he is fixed.
This is slide 9. Yeah.
Yes, yes. Okay. Another question for screw axis about how I know where to position point P.
The point
slide, I mean 14, I think. Slide 14.
This one, or this one? This
14.
One. Yeah?
Yes.
This one. Yeah.
Where I must, in order to apply this notation, I must know the position of point P.
The question is at the other side. You know, you have a point of interest P. For example, in a robotic manipulator, the end effect of the robot is very important. So we know the point P. When we know the point P, put the fixed frame on top of that.
Oh, okay. Okay, thank you.
Very well. Let me just give maybe one or two slides. If there is any other questions. Zahra is not with us. Usually Zahra has some question, I hope. Yeah, I think that Zahra is not with us. Yeah, perfect. Let me go through, now that we have given, let me just go and review from the beginning. As you see, we would like to have motion of the fingers here. So we have the velocities here. And we would like to write. We have very important issues of writing. So we need the velocity representation. The angular velocity is defined by a screw axis. The relation between the angular velocity and the rotation matrix is given by this relation. You can highlight that. We know that Euler angle rate are not equal to the omega or the angular velocity, and we have the hassle to find the E and work with an E. We have a golden rule, very important. The most important and significant part of this part is this golden rule that we would like to use it for several different differentiation, and we have used that to proven that omega cross is R dot times R inverse. We have a velocity P in general, and we have to define the twist angle as a concatenation of the angular velocity at the top and the linear velocity of a point P of our interest at the bottom. This is a general formulation, and usually we use these two simple formulation. If you didn't find all the details here, there's no matter, no problem for the first robotic case. But these two cases you should learn quite easily. Now, we would like to go to the Jacobian. And I would like to talk about Jacobian. You are familiar with the name Jacobian in control. Usually for linearization, we use Jacobians and different ways. Hussein is putting his camera on. Please take off your camera, Hussein. Now, if we look at the Jacobian definition, as we had before, we have a forward kinematics and inverse kinematic in terms of joint space and task space. If we go the joint space and task space in differential variables, if we consider q dot and x dot or chi dot, x dot, a tuple of 6 by 1, you remember something that would give the position and orientation of the angle or of the end effector here. Very, 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 very similar to what we defined here as a twist, angular and linear velocity here. We had before that for the position, the joint space position. Let me just take off. Now, if you look at that, you see that the joint space variable q dot and task space variable chi dot or x dot, this is the relation between these two parameters in differential kinematics is related with the Jacobian. Jacobian is a matrix, a very important matrix. It is basically configuration dependent, that when q dot is given, you can find x dot or chi dot by just simple manipulation of Jacobian 2 times q dot. This definition is for serial manipulators, not for parallel manipulator. For parallel manipulators, we have a different approach to do that. Now, look at this problem in terms of mathematical formulation. We call x dot is equal to jq q dot. The forward map is related by Jacobian, and the inverse, if we have a fully actuated manipulator, a square Jacobian matrix, then we have inverse of J as the inverse manipulation. If it is not squared, we use a pseudo inverse here. We will talk about that later in the inverse problem. But how we can find the Jacobian? The Jacobian can be found in several ways. The first and important, or the definition case is, if we have the forward kinematics is a nonlinear map. If we find the forward kinematics in terms of a loop closure equation, and we define it for many different robotic systems, and usually the position of the end effector was a function of q1, q2 to qn, the motion or the motion representation of the angular map here. So when we have the joint variables here, we have the task variable here. If we use the golden rule and we have the derivative. Find the derivative with respect to time with respect to a fixed frame. If we find the derivative of that with respect to a fixed frame, of course we can also have to another frame, but generally to a fixed frame, then we can see that by just simple mathematics. A nonlinear problem derivatives gives you partial of f with respect to q1, partial of f1 with respect to q2 to qn, and this is a multivariable function f, so f1, f2, and so forth and so on. And then you can find all these variables sitting into a simple vector, which we call it a Jacobian matrix. So linear or kinematic relation is quite hard in terms of differential, in terms of representation. But when we come to the differential kinematics, usually and simply defined matrix can give the relation between q dot and x dot. And our problem and our issue in the next section is how to find Jacobian matrix of a robot. First, how to find it, as we see here, then see how it is related to the other issues like the force or the singularity or other relation that we will discuss. It very, very, very interesting and beautiful things that we will see in here. But here it is very simple and mathematical displacement. Now, this relation, let's talk about a simple example. I'll just give this motivating example, and that's all. We have a 2R manipulator. The first and simplest way to define a manipulator like that, and we find the relation between the velocity of the end effector, which was xe ye dot in differential term, with respect to q1 dot q dot, which is theta dot 1 in t2 dot 2. How we can do that? Very simple. We had the kinematic before, forward kinematic before. Xe is equal L1 C1 L2 C1 2. If you go to the previous section, we have defined the shorthand term kinematics in here, and ye is equal to here. Component wise, we simply make the derivative, time derivative xe dot is, and ye dot will be the derivative of this term, which is this one, and derivative of this term, C12 gives S12 theta dot 1 plus theta dot 2. And y dot with the simple S1 is give you the C1, and this goes to this. And if you have this relation, just factorize theta 1 and theta 2, like here as Q, theta dot 1 and theta 2 dot 2 as Q dot, and Chi1 as this part. The relation comes to a matrix here. And we have a matrix L1 S1, L2 S1 2, L2 S1 2, L1 C1, L2 C1 2, L2 C1 2. A 2 by 2 matrix. And the control people like matrices very much, because the matrices has eigenvalues, they have eigenvectors, they have determinant, they have norm, they have many, many issues related to them. We have a matrix here, which we call it the Jacobian matrix for this simple case. And as you see, this Jacobian matrix is Q dependent, is a function of Q, is a configuration dependent. This Jacobian is different at this point or at this point, and you can find different issues on that. And it is very, very important how we can find this. So the first way to do that is to find the forward kinematics and take the derivative and find the Jacobian matrix on top of that. But this is not usually simple. To find the Jacobian, we might find a simpler way to do that. Of course, in the books, especially in the Craig books, like to do that in terms of an iterative way. I don't like that. And I would like to use some more specific ways, especially with the Denavit-Hartenberg or the screw-based coordinate, to find very simple and very general form without solving or finding the derivative of the kinematic structure to find the Jacobian. Although the definition is the derivative of the kinematic relation, we will find methods to have the Jacobian find in a general way. I will discuss about this issue hopefully on Tuesday. If there is any question or comment, please give me your comments. And also it is good to say how did you find my voice and the video? Was it good or it has intermittently with problems? Any questions? Okay, if there is no question, like always, I have my office hours just after the class. If there is any other question, please join me on the Skype with the Skype link after the class. I wish you very, very prosperity and healthful year, full of success and fruitful result, and wish you all the best. سال نو رو به همه تبریک میگم و آرزوی سلامتی تندرستی برای شما و خانواده‌تون در این سال دارم. سال گذشته سال سختی بود، امیدوارم این سال سختی ها رو عبور کنیم و با موفقیت بیشتر و با سلامتی کامل سال خیلی خوبی رو برای شما آرزو میکنم. موفق باشید بچه‌ها. خدا نگهدار.